Okay, so let's go through this problem and see if we can figure out what to do. We start off with a boy diving off a cliff with a running horizontal velocity of 8.6 meters per second. The distance from the edge of the cliff to the surface of the lake is 12 meters. So the idea, well, this is our initial setup. They've provided a diagram, but this is essentially what we would draw given the description here. We know this height is 12, and we know that the boy is running with an initial velocity v0 of 8.6 meters per second. So we could write 8.6 up here. Okay, so how much time will it take the boy to fall from the edge of the cliff to the surface of the water? Now, this is a important distinction here. We need to realize that the boy's horizontal velocity is going to do nothing to his vertical displacement. Okay, so we can begin our problem by saying that we're going to use this equation here. I'll replace the x with a y because we're talking about vertical displacement. And I'll quickly just write up a little, we'll call this positive y and this positive x. And that gives us a coordinate system that we know is going to be consistent with what we're doing. So we know after the boy leaves, he's going to have a downwards velocity, Vy0 of 0. We know that after he jumps off, he's going to have a downwards acceleration, ay0, the acceleration is the same all the way through, of negative 9.8 meters per second. And that's because the acceleration is pointing downwards counter to the positive y direction. And we also know, well, that's actually all we need to know at this stage. We know he's going to be dropping this amount. We can decide what we describe as 0. I'll describe the bottom here, this location here as 0, and this location here is 12. So that would be the y value of 12 and a y value of 0 down here. So if we think of exactly where he's starting, y0, we can see that the boy is actually starting up at 12. So now we can use this information to use one of our to input into one of our equations and solve. So we've got y equals y0 plus vy0 t plus a half ay t squared. And that's just one of our kinematic equations describing position with initial velocity and acceleration. So let's input some values and see if we can solve this here. We know our initial position y, or we know our final position y is going to be when the boy reaches the bottom, because he's going to kind of do this motion here. So that's going to be 0 equals 12 plus Vy0, which is 0. So 0 times time is 0, so that's gone, essentially. And then we've got a half ay times time squared, but that's really going to be a half times negative 9.8 times time squared. And that's our equation that's describing the velocity, or describing this boy's vertical displacement as a function of time given these initial conditions. So now all we do is get to the point where we rearrange this, so that's going to be 12, or negative 12 equals negative 4. Do this in my head. 4.9 t squared, and divide both sides by 4.9, and we end up with, well, we end up with 12 over 4.9 because I'm being lazy, equals t squared. So that means that the square root of 12 over 4.9 equals t. That ends up being 1.4 1.56, if we're going to 2 decimal places, 1.56 seconds equals time. That's seconds, S. And that's it. That's how long it takes the buoy to reach the surface of the water. Notice that I did not include any of the 8.6. The 8.6 was kind of a non-used value because that's just the buoy's initial horizontal velocity, and his initial vertical velocity is actually 0. And in this situation, when we're looking at our vertical distance traveled or our vertical drop in height, the only thing that's going to concern us is our vertical components. In this case, we're calling those y using this coordinate system that I decided on at the beginning of the question. If you decided to change your coordinate system, for example, pointing y downwards and x to the right, absolutely fine. You just would have had some negatives as positives and positives as negatives. Okay, so B, how far from the cliff will he strike the surface of the water? Now we're going to use this value 8.6. This is going to be a key part of what we look at here, and is this value 8.6. So let's take a look at how we're going to do that. I'm going to see if I can select some of this stuff. Oh, this is just panning. So selecting this. Let's do full screen. Okay, so I'm just going to shrink this down a bit. Move it over to the side, and that gives me a bit more room to work in. I'll put this down here actually. So that's our initial problem that we went through. So now let's go back to the pen. And then let's continue with this problem. How far from the cliff will he strike the surface of the water? So we know that he's going to be in the air for 1.56 seconds. That's a given value. That's a given value. He's going to be in the air for 1.56 seconds. We just calculated that because that's how long it's going to take him to drop. Well, he's traveling horizontally during that time at a constant velocity of 8.6. Now remember that that horizontal velocity doesn't change because there is no horizontal acceleration. Acceleration is just downwards, gravity. And horizontally, he's not actually accelerating or decelerating. So he's going to be traveling at a constant velocity of 8.6. So we can use a very straightforward equation. X equals x0 plus AT, no, not AT, VT, V0T, or in this case it's going to be Vx0, which happens to also be V0, times time. So Vx0, that equals 8.6 meters per second. So now we just put in some values. Oh, and we should probably identify some x positions. We will identify this location here as 0 in the x-axis, and then the x is positive to the right, so we're just going to have some positive value here. And essentially this is the variable that we're looking for, is that x position. So then we get x equals x0, which is going to be 0, plus Vx0t, and that Vx0 is 8.6, so that's going to be 8.6 times time, which we know is 1.56. And in this case, we can then have x equals whatever 8.6 times 1.56 is. 13.42 to 2 decimal places. 13.42 to 2 decimal places. And that's essentially it. That's how far he's going to go. That's going to be 13.42 meters, and that is our answer to B. So our answer to A was 1.56. Our answer to B is now going to be 13.42 meters. I did something that I probably shouldn't have done. I used 1.56 itself, the rounded value in my equation here. What we probably should do is actually use 1.5642492, or the unrounded version of the equation, and that would give actually a better and a more accurate value for what is going on here. What is the landing velocity? So now let's take a look at part C. So let's take a look at part C. So I'm going to minimize this, move this over. Oh, I missed the T. Let's select that again. Actually grab everything at the same time and minimize this. So now we're going to take a look at what the landing velocity is. So to find the landing velocity, what we're going to need to do is realize that he's actually got two different, well, his components of velocity are two different components of his velocity. He's got a horizontal component of 8.6 meters per second, but he actually also has a vertical component of whatever velocity in the vertical direction he has gained over that time, and that would be whatever velocity he's built up in that 1.56 seconds. We don't have that value right now, so we would really like Vy, right? The velocity in the y direction when he hits the ground, not his initial velocity, which is 0, but when he hits the water, what his vertical velocity is. And then we would add these two vectors together using vector addition, and this would give us our v, our final velocity, and this is the direction essentially he would be actually traveling in, and that would be the total velocity that he's moving. So let's go through that. First, we need to find Vy. Now we've got two equations that we could use. We can use the V equals V0 or Vy, I'll put the components in there, Vy equals Vy0 plus Ay times time, so the acceleration in the y direction times time plus your initial velocity would give you your final velocity, and we know time now. We calculated it. It's 1.56. We also have the option of not using this time, of actually using this equation, Vy squared equals V0y, or Vy0, sorry, squared plus 2ay times y minus y0. And this equation would actually should give us the same value, but notice that it is not including time. And so this equation is not including the time that I calculated. Given the option, you should always go for work or processes that use your calculated values as little as possible, because if you'd made a mistake here, it would move on to the next problem and you'd be using that time. Now, error carried forward will be graded as correct values. So if you'd screwed up the time in the first part, that doesn't mean that all your subsequent values would be incorrect, but what it would be good to use an equation that you have not, that doesn't include calculated values. So let's go through this. If we use this equation, we see that we actually have all of this information already. We know that he's going to go 12 meters, so that's going to be 12 minus 0. We know his acceleration is negative 9.8, and we know his initial velocity is 0. What we're going to be looking at is his final velocity. Well, we'll go through this. So his final velocity, Vy squared, is going to be equal to, this is 0, so that's 0, 2 times negative 9.8. Now at this stage we might be thinking, well, this is going to be 12, because that's how far he's gone, and that would give us a negative value, and we can't square root negative values. However, we've got to be careful. his initial position, y0, was actually 12, and we've written that down up here. His initial position is y0, which means that his final position is 0, which means that that's actually 0 minus 12, giving us a negative 12 in this, meaning that we get Vy squared is equal to 2 times 9.8 times 12, once the negatives cancel each other out, which is a positive value. So Vy squared equals 235.2, 235.2, and if we square root that, Vy ends up being equal to 15.34, 15.34 to 2 decimal places. And that's about it. So that's our velocity that ends up being meters per second. That's our velocity for our vertical velocity here. So now I'm going to move over here and do the Pythagorean theorem so we can do our vector addition. That's going to be 8.6 plus, or this component here, 8.6, plus this component here, 15.34, but we can't just add them together. That's that's the square root of 8.6 squared plus 15.34 squared, which is actually 235.2, so that's actually not that big of a problem. So it's actually kind of nice that we've got this 235.2, which is really this already squared. So that's why you don't see the squared here. And that ends up being 17.58. So 17.58. And that, so 17.58 meters per second is our actual velocity. That would be v. Our actual velocity is 17.58 meters per second. And that's going to be this guy here. That's it for that. So here, what's the actual velocity? 17.58 meters per second. And now, graph the horizontal and vertical components of the velocity. What we're going to do, I'm actually just going to scroll down for this one. So graphing the horizontal and vertical components is relatively straightforward. If this is Vy, actually I should give it a negative as well. And this is time. This is Vx. This is time. So velocity y is actually going to start at 0 because our initial position, when we jumped off the cliff, our velocity here was 0, and velocity y got bigger, but it's actually pointing downwards, and that's against, or that's the other direction from what we decided was positive. So that's actually going to start at 0 and become negative. And after 1.56 seconds, 1.56, it becomes 15.34. 15.34. And so this is in meters per second, and this is in seconds, measured in seconds. So meters per second, seconds, and 15.34 meters per second after 1.56 seconds. Our velocity in the x direction is going in the positive direction, because that's what we decided positive was. And that's going to stay at a consistent 8.6. It's going to stay at a consistent 8.6. So our velocity in the x direction is just going to be here. We'll describe with the value there of 8.6. And at this time here, we've got 1.56. Notice that I've stopped the graphs and I haven't continued them onward. After this time, we really don't have enough information to continue with our problem, because we don't know what happens to the boy after he hits the water and exactly how he slows down, and that's beyond the scope of this problem. But this would be that final section where we've graphed our velocities and our components of our velocities, Vy with respect to time and Vx with respect to time. And that's it for this question.